Sampling theorem. Let the bandwidth of an analog signal be Fmax. If it's sampled at the Nyquist rate, then the original signal can be obtained by passing the digital samples through a digital to analog converter, and then an ideal analog low-pass filter. Okay. Aliasing. If the signal is not completely limited to the bandwidth of Fmax, then the high-frequency components of Fs over 2 or half Fs will fold back and will appear at a different frequency in the signal samples. This property of returning to the lower band is called aliasing. It creates a noise-like effect, and aliasing is creating a false low-frequency signal. The spurious signal is the result of an insufficient sampling rate of a high-frequency signal. Very important definition. Now, anti-aliasing filter. Unwanted frequency components can be attenuated before sampling using an analog filter. The design of such a filter depends on the amount of acceptable mixing noise. For example, we can use a Butterworth filter with degree of n. Here you see the absolute value of h of f, or amplitude of the low-pass filter, which is equal to 1 over square root of 1 plus f over fc to the power of 2 times n, where fc denotes the cutoff frequency, wherein the amplitude will be 1 over square root of the maximum amplitude in passband, or the power will be half of the power in passband. Both the same. We remember from the Signals and Systems course that the spectrum of an analog pulse in the time domain will be equal to a sinc. Also, the spectrum of a sinc in the time domain is equal to a pulse. On the other hand, an ideal low-pass filter has a spectrum in the shape of a pulse. It means that the impulse response of an ideal low-pass filter becomes a sinc in the time domain that extends from minus infinity up to plus infinity, which means that it cannot be realized in practice because it happens forever. As a result, its length should be limited. A solution is to multiply sinc by a time window. On the other hand, we know that the multiplication of two signals in the time domain is equal to the spectrum of convolution of those two signals in the frequency domain. As a result, instead of pulse, we will have a tolerance scheme for the spectrum of the low-pass filter, as depicted in figure 2.2. A low-pass sinc in time domain, the spectrum of windowed sinc. Okay? These are called repels. Tolerance scheme of a practical low-pass filter is the caption of figure 2.2. Now, tolerance scheme for a low-pass filter. Here is passband up to some point, and here is called stop band, and this area from Fc up to Fs is called transition region. Okay? Now, figure 2.3 shows the common terms used in a tolerance scheme. Okay. Passband shows the pass region of the practical low-pass filter, whose frequency ranges from 0 up to cutoff frequency Fc, denoted as Fc. Stop band demonstrates the attenuation area by the practical low-pass filter, whose frequency range is from the edge frequency of the stop band, denoted as Fs, up. Please consider the difference between Fs and the capital Fs, which stands for sampling rate. And transition region refers to a region whose frequency range is between cutoff frequency Fc and the stop band frequency Fs. Okay, let's continue. The shorter this area is, the better the quality of the filter, because this band in fact defines the area of indecisiveness in terms of passing or not passing. On the other hand, for a high-pass region, the degree of the corresponding filter should be increased, which in practice will face implementation limitations and increase the cost. Okay. Take home 2.1. Find and plot the tolerance scheme for high-pass, band-pass, and band-stop filters. If an analog signal passes through this low-pass filter, in the worst case, that is when the signal has all frequency components, the signal spectrum at the output of the filter will take the same form as above, because the signal spectrum is multiplied by the filter spectrum. Here a very important illustration showing aliasing level. Please look at it. Blue color and yellow color. Just here is 0 and here is Fs. We have completely a periodic spectrum repeating from 2 pi or Fs sampling rate, right? And here it's called aliasing field frequency from cutoff up to Fs minus Fc. Okay? Therefore, after sampling, the spectrum of discrete time signal will be the same as the spectrum shown in figure 2.4. It means that aliasing is unavoidable for practical filters. Right. In this case, the relation among sampling frequency, denoted as Fs, filter cutoff Fc, and aliasing frequency Fa will be Fs greater than or equal to Fc plus Fa. On the other hand, the relation between the sampling frequency and filter's stop band frequency is Fs needs to be greater than or equal to 2 times stop band frequency, or Fs. Okay. Proposition 2.1. Having R being equal to 20 k ohm and C equal to 10 nanofarad for anti-aliasing filter in figure 2.5, determine the minimum sampling rate such that we have an aliasing error of less than 2% of the signal level in the pass band. Okay, have a look here. R cascaded with C. If there was no op-amp, it would have been called a passive low-pass filter. But when we insert op-amp between this point and the output point, there will be a strong buffering from output to input or vice versa, the impedance in the input will be infinity, while the impedance in the output will be about zero. So we have buffering. Anyhow, it's called an active low pass filter. Anyhow, it was just a point from electronics course. Now, solution. According to the relation among voltages and currents, V plus will be equal to V minus equal to x2 of t and equals to 1 over Cs. S stands for Laplace transform over 1 over Cs plus R. What does it mean? The impedance of capacitor over the sum of impedances times input or x1 of t. No, considering that S is equal to J capital omega, the frequency response of the filter will be as follows. H of J omega is output spectrum over input spectrum, or say it after simplifying 1 over J times capital omega times R times C plus 1. Okay? Therefore, the range of angular frequency response is equal to amplitude to the power of 2 will be 1 over omega to R, omega to the power of 2, R to the power of 2, C to the power of 2 plus 1. Right. Consequently, considering omega is equal to 2 pi f, it can be written that abs of h is equal to 1 over square root of 1 plus f over fc to the power of 2 times 1. The degree of the filter is here 1, so 1 is not written. We know that the amplitude in cutoff frequency is equal to 1 over square root of 2. So, cutoff frequency will be about 796 Hertz. Considering the acceptable level of aliasing, which is 2% of 0.7, we will have here, look at FA, we will have FA approximately 56 kHz, or sampling rate roughly 57 kHz. Okay. Proposition 2.2. If we use a fourth order Butterworth, meaning that we try to increase the degree of the low pass filter in the previous example, what would be the minimum sampling rate for the given specification? So again, these are level aliasing level the same. We will have, considering the degree of the filter here, we will have FA roughly about 2.3 kHz, a considerable reduction, or FS about 3.1 kHz.